Chemical bonding. Ionic bonds. There are two types of chemical bonding. One is called intramolecular forces and one is called intermolecular forces. In intramolecular forces, we got three types of bonds: ionic bond, covalent bond, and metallic bond. But for now, we will study ionic bond. So ionic bond is a type of chemical bond formed through the electrostatic attraction between a positively charged ion cation, usually the metal, okay, and a negatively charged ion, anion. This typically occurs between metal and a non-metal. So you have to remember that ionic bond is a transfer of electron from a metal to a non-metal, and the metal will become positively charged while the non-metal will become negatively charged. For example, let's say metal sodium, like sodium lose electron to form cation or cation, and non-metal like chlorine will gain electron to become anion. So the metal will lose electron while the non-metal will gain that electron. For example, sodium transfer one electron to chlorine, forming Na plus and Cl minus. These oppositely charged ions attract each other, forming NaCl table salt. Key features: formation of crystals. So ionic bond usually form crystal lattice structure like NaCl form a cube-shaped crystal lattice. For example, this is known as by like just like a cube. It makes something like cube like this. This is how its structure look like. High melting and boiling point. So due to strong ionic bond, they have high melting and boiling point. Ionic bond are often dissolved in water and polar solvent like water. So they easily dissolve in water. And electrical conductivity, they conduct electricity when molten or dissolved in water as ions are free to move. So if they are in solid form, they will not conduct electricity. If they are in liquid form, they will conduct electricity easily. Energy consideration: ionization energy. Energy required to remove an electron from a metal, and electron affinity. Energy released when a non-metal gains an electron, and lattice energy. Energy required when ions came together to form the crystal lattice. Ionic bond. So you see here, sodium is transferring this one electron to chlorine, and now you see here, chlorine has got one extra electron. So the chlorine outermost shell is completed, and so for sodium as well. This is the crystal lattice structure of sodium chloride, like sodium chlorine, sodium chlorine, sodium chlorine. Covalent bonds. Now in covalent bond there is a slight difference. Okay, so there is shaving up electron, one or more pairs of electron. In ionic bond there was complete transfer of electron, and often a full. Okay, so they achieve a stable electronic configuration of often a full outer shell octet rule, and it usually happens between non-metals. So electron sharing, atoms share valence electron to achieve stability. For example, H2O, each hydrogen atom share one electron with oxygen. Now there are three types of covalent bond: single, double, and triple. So single covalent bond mean one pair of electron is shared. For example, in case of HH, KH bond H. Now, in case of O bond O, this is called double covalent bond, and N bond, triple bond N is known as triple covalent bond. Polar versus non-polar. Polar mean equal sharing of electron. For example, Cl2, like they will share the electron equally, while non-polar will have unequal sharing of electron due to difference in the electronegatividity. For example, H2O, where oxygen pulls the electron closer. Molecular shapes, respectively. The 3D structure of covalent molecules is determined by the repulsion between electron pairs. For example, carbon dioxide is linear, H2 is bent, and BH3 is trigonal planar, and CH4 is tetrahedral. Physical properties: they have low melting and boiling point generally as compared to ionic bond, and poor conductor of electricity. And they can be gases, liquid, or solid at room temperature. For example, oxygen is gas, hydrogen, water is liquid, and sugar is solid. This is example of covalent bonding. Hydrogen need one electron to complete its shell, and oxygen need two electron to complete its shell. So they share those electrons, and now they have a complete outer shell, all of them. So it is a happy family. Metallic bond. The third type is the metallic bond, and a metallic bond is a force of attraction between the free-floating delocalized electron. So there is delocalized electron and the positively charged ion metal cation or cation in a metal lattice. The C of electron allows metal to exhibit their characteristic properties like conductivity and malleability. So feature they have C of delocalized electron means in metallic bond valence electrons are not bound to individual atoms. So the valence electrons are given to the C of electrons and structure usually have crystal lattice structure and properties. They are good conductor of heat and electricity because they have free electrons, and they are also good conductor of the thermal conductor, and they are malleable and ductile and luster. They have free electrons reflect light, giving metals their shiny appearance. So this is a sea of electrons. You see here the dots are basically electrons, and they are being given by the valence shell of the elements which are present in the bond. Bond energy. Bond energy or bond enthalpy is the amount of energy required to break one mole of a specific type of bond in a gaseous molecule. It is measured in kilojoule per mole, and it is represented by the strength of a chemical bond. The higher the bond energy, the stronger the bond. For example, the H bond energy is 436 kilojoule per mole. Now we compare them with others, and then we see that if it is stronger or not. Factors affecting bond energy: higher bond order, single, double, triple means stronger bond. For example, carbon C double bond C 348 kilojoule. Now double bond 614 and triple covalent bond 839. So this means that for breaking down the triple covalent bond, it requires more energy. Bond length. Shorter bond length are generally stronger. So shorter the bond length, stronger will be the energy. Stronger are the bonds. For example, in nitrogen, triple bond is stronger than nitrogen double bond. Polarity. Polar bonds HO often have higher bond energy due to partial charges. Role of bond energy in the reaction. It helps determine whether the reaction is endothermic or exothermic. And the formula for this is bonds broken minus bonds formed. So we will add all the bonds which are broken, the energies, and we will subtract that from bond formed, and that will give us some value which will determine if the bond was exothermic or endothermic. Bond polarity. Bond polarity arises from an unequal sharing of electron between two atoms in a covalent bond due to difference in electronegativity. When there is difference in electronegativity, then there is unequal sharing of electron, which is refers to bond polarity. Electronegativity and bond polarity. When two atoms have different electronegativities, the shared pair electron are pulled closer to the more electronegative atoms. This creates a partial positive charge, negative charge, and a partial positive charge, and on less electronegative atom. For example, let's suppose there is HCl. So on H there will be partial positive because it is less electronegative, while chlorine is more electronegative. Here the example is given. As you can see here that HCl, the chlorine more electronegative, pulls electron towards itself. While in case of H2Cl2, same atoms have equal sharing, so non-polar, they are non-polar. So HCl is highly polar and H2Cl2 is non-polar. Types of bond based on polarity. So non-polar, equal sharing. In polar there is unequal sharing, and in ionic bond there is extreme difference. Okay, so in non-polar the difference is usually between 0 to 0.4, and polar the difference is 0.4 to 1.7, and ionic bond is more than 1.7. Dipole moment. A measure of bond polarity represented by an arrow pointing from the positive to the negative end. Stronger dipole means indicate higher bond polarity, as you can see here in this diagram. Electronegativity. Electronegativity is the measure of an atom ability to attract and hold into bonding electrons in a chemical bond. The concept was introduced by Linus Pauling, who developed the Pauling scale, the most commonly used scale. So fluorine is the most electronegative element according to that scale, which has 3.98 electronegativity, whereas cesium and francium have the least, which has 0.7. Why is it important? So it determines the bond polarity. For example, it explains the phenomena of hydrogen bonding, dipole-dipole moment, and acid-base behavior. Factors affecting. So acid base, smaller atoms have higher electronegativity since the nuclei exert a stronger pull, while nuclear charge, a higher number of protons increases the effective nuclear charge. Electron shielding. Inner electrons shield the valence electron from the nucleus. In a large atoms, electronic configuration stability. Elements with stable electronic configuration typically don't attract additional electron and have low or undefined electronegativities. Across a period, electronegativity increases, and down a group, electronegativity decreases. Special cases, noble gases generally have no electronegativity values, and lanthanide and actinide have low and irregular electronegativities due to poor shielding by f orbitals. Bond types: nonpolar covalent bonds and polar covalent bonds. So, in nonpolar, there is shared electrons are shared equally. For example, electronegativity is less than 0.4, while the polar covalent bond electronegativity is between 0.4 to 1.7. An ionic bond electronegativity is more than 1.7, as I told you before in the previous slide. Intermolecular forces. Now, all these forces which we talked about in the previous slides were intramolecular forces: ionic bond, covalent bond, and mm, metallic bond. Now, these are intermolecular forces. So intermolecular forces are the attraction or repulsion between neighboring molecules. Now they were inside a molecule. Now intermolecular forces is basically between molecules. While they are weaker than intramolecular forces like covalent or ionic bond, they play a crucial role in determining a substance physical properties such as boiling or melting point. London dispersion forces. It is the weakest of all. It is also called van der Waals forces, weakest and most universal intermolecular forces. It arises from temporary dipoles created when electrons in a molecule shift monumentally. So the electrons will shift to one side of the atom and it will bond with the another atom, but it is usually for a very short period of time. Increase with molecular size, more electron and surface area. And large heavier atoms exhibit strong London dispersion forces. For example, the noble gases argon and xenon condense into liquids at low temperature due to the dispersion forces. Dipole-dipole attraction is strong, moderate strength. So London dispersion is the weakest. Then dipole-dipole is kind of moderate, okay, and it happens between polar molecules. And the cause, the positive in of one polar molecule align with the negative in of another, resulting in electrostatic attraction. So this is the London dispersion forces. As you can see here, that the electrons are going more to one side of the elements. Okay, so partial positive and partial negative is made. Strength factor: stronger the molecule with higher polarity, a greater electrostatic electronegativity difference. Number three, in SCl and acetone, there is um, dipole-dipole attraction because they are polar covalent bonds. Now hydrogen bonding. This is a special strong dipole-dipole interaction. So this is the strongest of all, and it is a type of dipole-dipole interaction. It occurs when a hydrogen atom, remember, when a hydrogen atom is directly bonded to a highly electronegative atom like nitrogen, oxygen, or fluorine, creating a strong partial positive charge on hydrogen and a partial negative on most electronegative atoms. For example, okay, now strength factor: fluorine is more electronegative than oxygen than nitrogen, so the stronger the hydrogen bond. We will see in the next slide how it happens. For example, let's say there is a water molecule H2HOH, and there's another water molecule HOH. Sorry. So when there's this bonding, these dotted lines, this is when there's interaction between two molecules. This is known as hydrogen bond. But remember, on the hydrogen, there will be a partial positive sign, and oxygen, there will be partial negative sign. Example is water. Each molecule form up to four hydrogen bonds. Iron dipole forces. They show the strongest type of for intermolecular force. It occurs between ion and a partial charges. Significance: crucial in dissolving ionic compounds in polar solvent. For example, Na ions are surrounded by the partial negative oxygen ion, and magnesium ion exhibit even stronger ion. So the strongest of all is the iron dipole, then hydrogen bond, then dipole dipole, and then London dispersion forces.